We call it the ideal gas because it's dilute and it's something which behaves in a very simple manner. The molecules are considered to be non-interacting. The mean free path is very large. The collisions are elastic, things like that. So with all that idealizations, we saw that this quantity is given by this expression where you have the mass of the molecules over here and then the number density and this crucial quantity which is the average of the squares of the velocities. And then we also saw that if you want to recast this in the form of a very familiar empirical law, which is PV equals to NKT, then we immediately saw that you have to interpret this velocity square with the temperature, right? So this is what we had done in the last class, and then we asked this question as to how does one measure this mean? And for that we introduced the idea of a distribution function. I also gave a small problem. Did anybody try the problem? How many? Can I get a hand raising? Oh, that's a fairly small number, but anyway, still. So it's a very simple problem, so I want to just go through that in the beginning. And today we shall now be getting into actual thermodynamics, the laws of thermodynamics, and temperature to be more specific. So we'll try to understand temperature today. But let's discuss the problem we gave in the last class. So what we had was a column of gas, and we assume that the gas is at some constant temperature T. So, well, it's sort of wrong to assume that we understand T already, but well, you have some idea of temperature. So the gas is at some temperature T, and then we ask the question, how does the number density vary across height? So this is H, and if the gas is at constant temperature and follows this equation of state, this law, then how does the number density vary? This was the problem, if you remember. So the idea is very simple. Idea is based on the fact that the pressure at different heights would be different. And if you consider a certain height h and then take a little delta h over there, you can compute the pressure difference, or the pressure over here and pressure over here would be different, and how much would that difference be? So we can define the density of the gas as its mass of the molecules times the number density, and there is of course the constant gravitational field. So how would this delta P be? What would be delta P? The difference of pressure at these two heights, simple fluids, it's rho times G times delta H, and rho is m times n, so this is mn delta H. And this has to be now used in conjunction with this law. So we know that if you have, so actually this should not be n, this should be a capital N, the total number, because we have used the volume here. So clearly you can see that delta P would be K times T, temperature is constant, proportional to delta N. This will be, you can write it as nRT, number of moles, RT, so that can also be done. So now when you substitute, what do you get? Delta N by N is the quantity that we want to find. There is a slight problem fact that the gas, as it goes up higher in altitude, the pressure here and pressure here, which one do you expect to be larger? Right, but H is measured in the vertical from 0 on, so there is a minus sign that we have to take, and so finally you have delta N by N equals to minus mg delta H by kT. So if you can simply integrate this, you will get N, so you get log N when you integrate, and this is minus mg H, where H is measured from some reference height by kT, and you can write this simply as plus some constant. So you can simply write this as some constant N0 e to the power mgh by kT. So this is the law. In fact, this is a very famous law, how particle densities just fall off exponentially as we go higher and higher up. So the decrease is exponential, but that's only provided that all the molecules are at an average temperature T. Yes?
Shouldn't that be R?
I think it's K. It's fine. So let's just clarify this. So this N is number density. This is the number density. So this is N by V. So if you write this in terms of, so this is fine actually. This is R. So you can use R. It's okay. This R and K are basically related by Avogadro number. R is basically, or K equals to R by the Avogadro number. So it's basically the same thing. There's nothing more physically more important than the difference between R and K are not too much, because it's just a choice of units. Now this is okay, but the main point is we are still not getting to the point where we are being able to calculate the distribution function. Let's try to understand what the distribution function really means. So if I ask this question, velocity or speed of the particles of gas equals to 2.3729 meters per second, and ask this question, how many molecules are having this speed? Is that a good question to ask? Somebody said last time that is just not a good question to ask. We should talk in terms of the speed intervals. So you should talk about a speed v and speed v plus delta v, and ask how many molecules are having velocities in this range. And that quantity is what we had defined as dn with a subscript v, and it's called the distribution. I'll give an example for you to understand this point. dn, which we call the distribution function. Let's try to understand this. I take an example. Let this function be linearly proportional to velocity. Let it be some constant times velocity. Is this allowed? Do you think it's an allowed distribution function? Why not?
Because velocity at very large velocity, then number of particles would be very large.
Right, so what it essentially says is that this distribution will just keep growing linearly. At high velocities you will have arbitrarily high velocities, an arbitrarily large number of particles would be having those velocities, which is what we don't expect to see in real life, right? So this function, this distribution, should be something which should have a minimum and a maximum. The minimum, of course, should be at the point where velocities are very low, near zero. Do you think this should have a maximum? This quantity should have a maximum. What would that correspond to? So, by definition, when this quantity has a maximum, it means the largest number of particles are having velocities around that point, right? So that's the most probable situation. And then at very high velocities, it should also be very small. But I can always construct some strange distribution by saying that, well, at very high velocities, the distribution is 0. At very low velocities is also 0. It's 0 here and 0 here. There are no particles having very high velocities and very low velocities. And in the middle, there is something like this. Now, is this a reasonable distribution function? Why? Well, this is still fine. I mean, it's not really that bad. Because, yes, what is your? Every?
Average velocity, it will be very high.
Well, here it is low. You have some velocities where there are a small number of particles. Well, it reaches something like this. And then beyond a certain velocity, there is no distribution. There is no particle. Okay. How does it matter? Why should continuity be an issue? Absolutely. I mean, he has the point. There is some natural cutoff velocities. I mean, why should there be two velocities in the system naturally which are so unique, right? That no particle goes below this and no particle goes higher than this. I mean, that's perfectly arbitrary, right? There's no reason why should there be some natural scales of velocities in the distribution. So clearly it cannot be like this. You can see that if I give you this, you can still compute various numbers. You can compute, for example, average quantities, because you know a distribution function, you can compute average of velocity square, average of velocity cube, and things like that. But physically this is most unlikely that this is the kind of distribution function that you will have. But if I, for the time being, just take this as a toy model, a wrong model, but it's still a toy model, to calculate average quantities, what would be the various steps you should have to follow? The first thing is that, can this k be arbitrary if this has to be a distribution function? This constant? Can this k be arbitrary? How would you fix this k? If you have to fix this k, how would you do that? What is the condition that the distribution function has to satisfy? This denotes the number of particles having velocities between v and v plus dv. My question is, how is it going to fix this number k?
Like keeping the temperature constant.
There is no temperature as yet. I have not introduced any temperature. Just from this information. Just that. It's all right. I think we can keep that off for a while. Anyway, so I was wondering that I didn't joke, and there is already a joke. It violates causality. So, I mean, maybe I'm looking funny or something. How do you calculate this? The main thing is that this quantity dnv for all velocities should give you the total number of particles. So there is a big constraint. The total number of particles are fixed. So the moment you have fixed this condition, you can always calculate this constant k, just by using the condition that no matter how the distribution is, the total number will sum up to the total number n. Great, so for this distribution you can immediately find what this v is. So if I say that, okay, this is, say, v1 and this is say v2 and some strange velocity scales, I can integrate this between v1 and v2 and I can find this k. What would k be in this case? Very simple to integrate, kv. kv. So it's like k v square by 2 and it's evaluated between v1 and v2. This should give you n and from here you can fix the value of k, as simple as that. Once you have found the value of k, then you have a distribution function dnv completely specified, and the rules for calculating averages of any quantity that depends on velocity, for example v square, v cube, v, so on and so forth. Any quantity that log v, well log v would be funny, so log v by some v0, dimensionless. So any of these quantities that you are probably interested in, you can find the average if you know this distribution. And the rule to find the average of any quantity is basically to sum, which is the integral in this case because it's a continuous variable, of the distribution function multiplied by whatever you are trying to find the average for. So if it's v square, it's v square. So this is going to give you a v square average. If it's v cube, you just put v cube. If you know this function, you can integrate and you get the average. So that is the whole point. Now let me see if I can. Okay. So this was the problem, we solved it today. I would urge you, this is not mandatory though, to look at the chapter 40 of Feynman Lectures Volume 1 and just read through these two sections. It's a very beautiful way of analyzing this distribution of gas molecules in an air column. So please look at this and it's very beautiful, the treatment by Feynman. So in fact, he gives a very non-rigorous way of arriving at the distribution function for a gas at constant temperature. It's not the most rigorous way of doing it. The rigorous way of doing this problem actually requires knowledge of a subject called statistical mechanics. Since that is not a part of this course, we shall not go into the derivation. But I would still urge you to look at the Feynman's arguments and how he looks at it. It's good. It's a good reading. So what turns out is that the distribution for molecules in a gas is given by this function. As you can see, it's a continuous function and it has a peak and then it has two tails, which is exactly what we want. So essentially it is in the nature of this function v square e to the power minus v square. If you look at this function, this has that shape that we are interested in with a central peak and two tails, which is how the distributions are, distribution of molecules go for velocities ranging from 0 to very high values. Now what is important is the fact, and this is what we saw in our problem too, that there's an energy, in this case mv square by 2, and there is this kT factor. So this exponential has v square by kT, and there's an m of course, which essentially tells you that this temperature, and if you fix the mass of each molecules, if you just say that the mass of the molecules are same for all the molecules and they don't change, it is solely the temperature and nothing else that completely fixes this function. If you just choose one temperature, this entire function is fixed. There's just a single parameter which fixes this entire function, this entire distribution. What it essentially means is that if I give you the temperature, if I give the value of this quantity over here, you can completely draw the function without requiring to know anything else. Of course, you have to know the mass, but you can assume that it's a constant. The rest of the things are just pi's and this universal constant k, so which are again something which are fixed. This point corresponds to the most probable speed. So the velocity over here, most probable, is the one corresponding to which this distribution function reaches a peak. And of course you can find it out by just doing some simple calculus and seeing that where the function actually turns. So the first derivative vanishes, you can find this number. And as you can see, there is nothing else that it depends on except for temperature, right? So when you increase the temperature, the mean will shift to higher velocities, which is exactly what you expect. So if you change the temperature, the mean shifts to a higher velocity. Now that is very understandable. You can look at the graph and it shows that it has moved to a higher velocity. T2 is greater than T1. My question is, can you explain why the green curve, which is for a higher temperature, why is that lower? Why is that actually a slightly less peaked? It's flatter. Right. Absolutely. Now, it's not just the shape. You have to always guarantee that the total number of particles that we are trying to distribute has to be a constant. So the total area under the curve, which is integral of dn. So integral of dn, this should be n, so which is the area under the curve, and that should be a constant. So if I say that at a higher temperature this shifts, and it comes here, this peak, and it broadens out, then it has to also get shallower. Why is it broadening out? Why is the distribution broadening out? This is the determining factor over here. In fact, if you have seen Gaussians, functions called Gaussians, they have a behavior like this, e to the power minus x squared by something called sigma squared, which is the spread of the function. So this temperature is directly related to how spread it would be, and as you can see, it is more spread when temperature is high. But if it's spread more, it has to also get shallow, so that the area under the curve is the same and you get the same number. All right, so we shall not go into the derivation of this formula. The rigorous derivation of this formula comes from StatMech, but as I said, Feynman gives a heuristic argument as to why this is what you should expect. So please go through those two sections in that chapter. So what have we achieved? Now this is an approximate formula for the distribution, because we have assumed only hard collisions, elastic collisions, and we have not taken into account quantum mechanics. We are not taking into account that these particles have electrons, they are charged, there is intermolecular force. We have not taken into account any of this. So it turns out that this distribution function is very crude and it's satisfied only in certain restrictive conditions. What are these restrictive conditions? One, we already mentioned that the gas has to be very dilute gas. The pressure is very low and the volume is very large. And also, the temperature is very high. So at high temperatures, low pressure and large volume, dilute, high temperature gas, this distribution is more or less fine. But when you go to very cold situations, when the entire thing condenses and you cannot avoid the use and the necessity to incorporate intermolecular interactions, and when quantum mechanics comes into play, clearly this will not be a valid expression. So all that is a subject of statistical mechanics, which we shall not go into. So what we shall take out of this is that we have understood, in some sense, temperature, which we saw determines the mean kinetic energy of the molecules. It also gives us the spread in the distribution of molecular velocities, and it's a single parameter with which we can actually get the distribution. So from the molecular picture, from the microscopic picture, the notion of temperature we get is clearly got to do with the velocity distribution. But when you do thermodynamics, of course, we have been using this PV equals to RT. That law, that empirical law, doesn't really require, that's an experimental law, doesn't really require you to look at temperature from this perspective, right? So when temperature was originally used in thermodynamics, people didn't really worry about where it comes from the microscopic picture. So we shall also take that route and see that in thermodynamics, when we introduce temperature, it is basically done keeping in mind some basic empirical results. And that is the most fundamental. In fact, it came after the first and the second, so it was called the zeroth law because it just historically came later, but it's more fundamental because it defines the temperature. So we shall discuss the zeroth law of thermodynamics now, and we'll try to understand how temperature from the zeroth law is basically what we shall relate to the same temperature that we have discussed over here. Okay, so we already have discussed a little bit of walls in our earlier class, in the last class. So to introduce the zeroth law, we need to understand again the nature of walls and the nature of thermal equilibrium. So when I said that there exist certain kind of walls which we call adiabatic walls, which doesn't allow any exchange of energy, then if you have two systems which you keep separated by an adiabatic wall, they don't talk to each other, and whatever thermodynamic properties they have at the state of equilibrium will just remain on their own. They will not talk. On the contrary, if you put a diathermic wall between the two systems, all the properties, all the thermodynamic parameters defining the systems will spontaneously change and they will acquire new values. That's the definition of diathermic walls. How do we understand temperature intuitively? Everybody would say the high school definition of hotness and coldness, things like that. Now, when I say hotness and coldness, I mean it's of course very vague, so we have to somehow nail it down to some properties of materials. What do you mean by something is hot, hotter, colder? These are intuitive ideas, so we need to understand what it really means, and then the next question will be how we can actually measure it. How can we measure temperature? Which basically tells you how equilibrium between systems is essentially a transitive property. Do you know what is a transitive property? Transitive property is A is related to B and B is related to C, implying A is related to C. Now it turns out that thermal equilibrium between systems is a transitive property, and thereby this one single statement, which is basically common sense, can be used to design what we call thermometers. So you have a thermometer which is in equilibrium with, say, seawater, and the same thermometer is in equilibrium with me, say, and then I can immediately say that I shall be in equilibrium with seawater. There would be no changes if I jump into seawater. Though we don't have to physically connect the two systems, by noting that they are independently in thermodynamic equilibrium with a third system, we can immediately say that they are in thermodynamic equilibrium with each other. And that's the zeroth law. So in the statement of the zeroth law, this is what we have. The green corresponds to diathermic wall, so there is exchange of energy, and the brown is an adiabatic wall. So this A and B are two distinct individuals. They have nothing to do with each other, and they have a adiabatic wall in between them. So their thermodynamic variables are independent and they don't talk to each other. And then through a diathermic wall, we are making them come to a state of equilibrium with some system called C. A and B do not talk to each other. They don't even see each other probably. But the fact that they are in thermal equilibrium in a state of thermal equilibrium with the system C immediately ensures that if I now put a diathermic wall between A and B, no changes will take place. It would be guaranteed that they would also be in a state of thermal equilibrium. And that is the statement of the zeroth law. Everybody understands this intuitively, but what we shall now do is to try to see that this very statement is what we can use to define what is called a temperature, and we can define something called a thermometer and devise an instrument called a thermometer and then measure temperature using it. So that's what we shall go into. Now let's try to mathematically understand what's going on over here. So when I say this statement, when I make this statement that A and B are in, or A and C, or A or B, B and C, any two systems you take, they are in state of thermal equilibrium, what does it really mean? What does it really mean mathematically when I say two systems are in thermodynamic equilibrium? First thing to note is that in the definition of equilibrium, we have the fact that the system is described by a set of thermodynamic variables. All right? So a system is described by a set of thermodynamic variables, and we took several examples. So for example, a hydrostatic system, the thermodynamic variables are pressure, volume, and temperature. So let's keep temperature aside because we don't know temperature as yet. So let's take pressure and volume as the two thermodynamic variables. Some other system could have, for example, a stretched wire could have the force on the wire and the length and things like that. So these are the thermodynamic variables, and they are only defined when the system is in equilibrium. Now when we have two systems respectively separated to each other, have an adiabatic wall between them, say another system. So this is one system A, this is another system B, and this has, say, values of these variables P1 and V1, or it could be F1, L1. And there is another independent system B which has its own set of thermodynamic variables P2, V2. There could be many other things, F2, L2. For example, there could be magnetic fields, there could be electromotive force. I mean, there could be many other things. It could be a battery, so it have electromotive force and things like that. So anyway, in the general case, you can just write certain number of thermodynamic variables for a system which have now been separated by an adiabatic wall. So you could choose any set of variables over here. You can choose any set of variables over there, and they don't talk to each other. The moment I say that I replace this wall by a diathermic wall, and these thermodynamic variables change spontaneously, and a new state of equilibrium is reached, I immediately can assure you that these numbers will all change, and now you cannot arbitrarily choose one of them. So they will be fixed. What it means is that when the entire thing is in thermal equilibrium, after some time you have lifted this adiabatic wall, put a diathermic wall, and all of these numbers will now change, and you won't be able to then arbitrarily change one of them. They would get related, right? That's what it means. So if I say A and B are in thermal equilibrium, it means that in that state, which is the state which occurs when I lift this wall, all the thermodynamic variables which these two systems have, they are related by some function, some relationship amongst each other, so that you have restrictions on the values that they can take. The whole thing is, of course, isolated. Both the things put together is isolated from the universe. So what you have when this wall is replaced by a diathermic wall is that you can say that there exists some function FAB, which of course depends on the two systems, and it basically relates the properties of the first and the second and connects them by some equation, P1, V1, P2, V2 equals to 0. So this 1 corresponds to the system A, the 2 corresponds to the system B, and then there's a function which says that you cannot arbitrarily change them. They're related by some equation. Now, let's come to the first part of the zeroth law. It says that if two systems A and B are in a state of thermal equilibrium with a system C, so let's try to write that down. So A and C are in thermal equilibrium, system A and C. So from there you immediately have that there is some function A and C. So PA, VA, PC, VC equals to 0. This is the meaning of A and C being in equilibrium. In the same way, when you say B and C are in equilibrium, you will have some different function F, B, and C. Of course, these won't be the same function, which is PB, VB, PC, VC equals to 0. This is the first statement, first part of the statement of the zeroth law. System A and C are in equilibrium, system B and C are in equilibrium. And now, what does it amount to? The zeroth law states that these two statements are the same as saying that now system A and B must be in equilibrium, right? When I say system A and B are in equilibrium, there should be a third function, which is A and B, which is now properties of PA, VA, PB, VB equals to 0. This is what it means. That's what it means. Now, look at this. These two statements together has to be the same physical content as this statement. They have to mean the same thing. That's the zeroth law. One follows from the other. So how can we achieve that? Look at this. Here you have only properties of A and B. Here you have properties of A and C. Here you have properties of B and C. Right? A and C in equilibrium, B and C in equilibrium, leading to A and B in equilibrium. If you look at this two, you can always do one thing. You can always write this equation in a slightly twisted form. What you could do is, you could just write it in a slightly different way. If AC function of PA, VA, PC, VC equals to 0 can also be written as PC equals to some different function of AC. And what would remain on this right hand side now? It would be PA, VA, and VC. So I've just somehow inverted this, brought this PC to one side. Now it's not necessary we would be able to do it for every arbitrary function, but let's assume that we can do this. And similarly from this, we could also write PC equals to some new function f of B and C now, which is function of PB, VB, and VC. And clearly if these both are PC, so they must be equal. Now you can immediately see what we are talking about. Equilibrium between A and B ensures that a function of a complicated form which involves variables from the first system, variables from the second system equals to 0. And then I see that the same thing also means that there is a function which depends on the first system, depends on the second system. And this VC is common to both, so you can keep it at constant. It's just a constant. You can keep it at some constant value. So what it means is that this function equals to 0 is the same as saying that you can split the A part and the B part. It is some function of A and some function of B which are now separately equal. So this function can be written in a form that as if there exists some function which only depends on A and some function which only depends on properties of B, and they are equal. So this property, which is equal when two systems are in thermal equilibrium, is the property of, what is this property? Temperature. So this function, which now depends only on the variables of the first or the variables of the second, that is what we call the temperature. So the temperature is that property of the system which is same when the two systems are in thermal equilibrium. So we just argued it in a logical fashion. This is very intuitive, but the zeroth law of thermodynamics can be recast in a mathematical form in this way. And what it allows us now is to define what are called thermometers. What is a thermometer? What is a thermometer? Everybody knows what a thermometer is. Something that measures temperature. Now, how do I measure temperature? I have just defined temperature as a property which is unique to the thermodynamic system, such that when that system is in equilibrium with another system, this property is the same. So before going into temperature measurements, we have to understand one more thing, the idea of an isotherm. Isotherm, same temperature. Okay? So if you understand what an isotherm means, we would understand how we can measure temperature. So for this, we take again two systems. These two systems could be any two arbitrary systems, and let's call these systems A and systems B as usual, and let's assume that the systems have thermodynamic variables which are, say, x and y. This could be pressure and volume or something else, and this would be some x and y, some other two variables, pressure and volume. The way to define an isotherm is as follows. I take an arbitrary state of the system B, which means a state in equilibrium which is defined completely by some values, say x prime, y prime. I fix this value. I choose this system to be in this state, an equilibrium state. And then I bring the system A to thermodynamic equilibrium with the system B, and I keep its one of the variables y fixed. The moment I fix y and I bring A in thermodynamic equilibrium with B, its x value will get fixed. That is what it means, right? There's a function which relates all the things, so its x value will get fixed. So this state of A is again an equilibrium state which is arrived when A is brought to thermal equilibrium with B, and that state and this state are in equilibrium. Now what I do is I change this y. This value of y was something I fixed, right? So I change this value of y to some other point, some other value of y. And I again look for the equilibrium. The moment I look for the equilibrium again, you will see there is a different state. This is x1, y1, x2, y2, a different state which is in equilibrium with the same system over here. And then you can keep changing y and you will get a whole range of x values. And all these points, if you connect, they will all be in equilibrium with the single state of the system B, and this locus is called an isotherm. So let me just give this one slide and end today's class. So this is the way to do it. You choose some x1, y1 prime, and then you get this whole set of points for A, and finally you change this initial condition, change this initial state to something else, another set of points over here. So you define the isotherms. So once we have the isotherms, we'll see how we can do thermometry and how we can measure temperature.